In this video, we're going to go over periodic trends, this includes talking about atomic radius, metallic properties, some chemical properties, and ionization energy. So a trend is a pattern. So a periodic trend would be a repeating pattern. And periodic trends and patterns are helpful because we can use them to predict things. So the first trend we're going to start with is the atomic radius, which is another way of saying the size of the atom. So if you look at this, this is just a portion of the periodic table. It's a visual where they've drawn different size circles to indicate the size of the atom. And in general, if you go from the left to the right on any of these periods, you'll see that on the left, we have the largest of the atoms in that period, and on the right, we have the smallest. So the atomic size decreases across a period. Then if we're thinking about the groups, the columns, if we go up a group, we'll notice, and you can look at any of the groups, that the largest atoms are at the bottom and the smallest atoms are at the top. And so the size of the atom decreases as you go up a group. So a generalization is that on the periodic table, we have the smallest of the atoms on the upper right-hand corner and the largest of the atoms in the lower left-hand corner. Now, I'm not particularly interested knowing the exact numbers or which is the smallest. It's more just of a trend to know how the atom size changes. Now, they don't include the transition elements in this particular visual because they tend to not have a strong pattern and sometimes even have exceptions to the trends we see in the representative elements. So we can explain the trends and that in the size. If we look first at number 1, this is the trend across the period. And if you recall, as we go across, it's increasing the atomic number, which means it's increasing the number of protons in the nucleus. So the positive charge in the nucleus is increasing. Well, if you recall from electron configurations in the previous chapter, as you go across a period, all of those electrons are in the same energy level. So as you increase the positive nucleus, the electrons in that energy level draw closer to that positive charge. So as a result, we see this trend that as you go across the period, the atoms get smaller. Now, the groups, I think, are easier to understand thinking about it going down the group. We were talking about it going up, but I think to explain it to me, it's a little easier to understand. We know that there's smaller atoms at the top of the periodic table and larger atoms at the bottom. And from our electron configurations, we know each time you go down to a new period, you add another energy level. So as you add energy levels, it's like putting on more layers. So as you add the layers, your atoms get larger. So at the bottom of the periodic table, the atoms have more energy levels and they're larger. At the top, they have less energy levels, so they're smaller. So let's use the trend to make some predictions. So here's the periodic table, and I'm just going to write the trends because I think it helps me answer. So what I know is as I go across the periodic table, the size decreases. So these are larger on this side when comparing them to the atoms on the other side of their periods. I don't want to say smallest. I'd prefer to say smaller in this example. All right, and then we know going up a periodic table that these are the, I'm not going to include, wait, I don't want to quite go down to the inner transition elements. Let's pause there. Let's go down here. So these are larger down here, and they get smaller going up. So we have this trend in mind, and then we'll answer the question. So it says, based on the general trends, all right, which one has the smaller atomic radius? So I'm going to compare letter A. Here's sodium, and here's potassium. So these two are in the same column, and I know that as you go up a column, the atoms get smaller. So since sodium is above potassium, sodium would have the smaller atomic radius based on the trend. So the next one, let's take a look. We'd have to find them. We're not worried about the numbers. We're not Googling, or we're just using the trend. So we have calcium and nickel. Now, in the previous slide or two when we started, the textbook left out the transition elements. But here now they have a question that includes it. So again, they've just told us to use the general trends. And the general trend is as you go across a period, because calcium and nickel are in the same period, as you go across, they get smaller. The atoms get smaller. So based on that general trend, nickel is getting further to the right. So I would predict that nickel is smaller than calcium. So I know they didn't show nickel and it said, oh, the transition elements have exceptions. But if we're just asked to use the general trend, we're not going to worry about that. We're going to say, okay, calcium is further to the left on that period, and so calcium would be larger than nickel. That's how we're going to predict. All right, so let's look at metallic properties. So metallic character means how much of the metallic properties does the atom have? And here you can read about the metals and nonmetals. I want to go back to this periodic table and remind ourselves that this stair-step line here is a divide, or can be used as the divider between, and on this side of the stair-step line we have metals, and on this side we have nonmetals. Hydrogen also is a nonmetal, which is over here. So that we know that, so just as a reminder. Now, the trend, so it's not like you're metal or you're non-metal. There's actually a trend, and the trend is similar to atomic radius. So the metallic character decreases from left to right, so across, and it decreases up. Okay, so I have a periodic table on the next slide that we're going to write this down in. Okay, so I'm going to get two different colors, and I might make it a little bit thicker here. All right, so let's do atomic radius first. Atomic radius, as I go across here, I'm going to draw two. Okay. I got to make it smaller to right now. I just wanted a little bit bigger line. So the atomic radius decreases, right? So that means these are the larger and these are the smaller. And if we go up and down, the atomic radius decreases as you go up. So these are larger, and it's on the top, it's smaller. Okay, so that was radius. We just did that one. Now let's do metallic properties. They said it was a similar trend, which means as we go, oh, let me make it a little thicker for this part, sorry. As we go across and as we go up. Okay, so if it's similar, oops, I want to go smaller. Sorry. Metallic properties decrease. So that means this is more metallic on this side, and this is less metallic. Whoops. And then it would be the same because they told us it was the same trend. Metallic properties decrease. Sorry. It's kind of filled in there. So down at the bottom, it's more metallic. Okay, so they have similar trends. So this would be my conclusion. Larger atoms are more metallic and smaller atoms, are less metallic. Not written very neatly, but that is my, oops, sorry, I got to go back. Oh my goodness, my hand's hitting it. I'm sorry. That is my conclusion, which means the nonmetals, which are smaller, have less metallic properties, and the metals are larger and they have more metallic properties. So larger atoms are more metallic and smaller atoms are less metallic. So let's take a look at how would we use this trend. Okay, so it says, based on the general trends of the periodic table, which is the most metallic? Okay, so I'm going to write the trends again just because this is how we think about it. So it decreases. So this is more, this is less. And as we go up, it does the same. So this is more, and that's less. Okay, so find tin and lead. Tin and lead. So these are in the same group. And we know that as you go up, it gets less metallic, which means as you go down, it gets more metallic. And they want the most metallic. So lead would be more metallic than tin because it's lower in the group. Then if we look at calcium and sulfur, so calcium is here and sulfur isn't in the same group. It's over. Okay, it's over and up. Okay, so as we go over, we're decreasing our metallic properties, and as we go up, we're decreasing. So sulfur is going to be less metallic than calcium. So we want the most metallic. So calcium is more metallic than sulfur. So again, it's about seeing where the trends are and then looking at the relationship between the two atoms and see if you can follow the trend to answer the question. So our next trend has to do with properties of the elements, and we'll be doing more with these kind of things in the next chapter. But let's take a look at some of the things we can predict. And Mendeleev used this particular thing to help organize his periodic table. So it says the properties of the elements follow regular patterns. That was noticed by the people originally in the early 1800s all the way up to the 1900s. That means we can predict unknown properties of an element based on those around it. Here's the really important concept here. Members of a group or family have similar chemical properties. That is important. Members in the same group, and family is another name for the group, have similar chemical properties. Here is an example below. It says all of the alkali metals have oxides of the general formula. So M2O. And here it's specific. So alkali metals are the ones in group 1A. So notice the formula is you have two of the metals with one oxygen. And so they go through all the alkali metals. They all have two of the metals with one oxygen. That is one of their chemical trends, a similar chemical property. So how can we use this to our benefit? It says metallic sodium reacts with chlorine gas to give sodium chloride. So sodium chloride is also an alkali metal. And notice there's one sodium and one chlorine. So its formula would be one, the metal, and then a chlorine. So it says predict the product form when lithium. So all of these, and potassium, these are all alkali metals. So they're in the same group, okay? That means they will have similar patterns. So this is the pattern. One metal, one chlorine. So we would predict that lithium would be one metal, one chlorine. And we would predict potassium would be one metal, one chlorine. Why? This is the chemical properties of elements in the same group are similar. So they would form similar compounds. Okay, so there's, I have another question along this same line. It says, and you can read it and pause and see if you can try to answer, or you can just go along with me. It says, which of the following metals has chemical properties most similar to zinc, which is Zn? Then it says iron, copper, or cadmium. Okay, so what we know is that elements in the same group have similar chemical properties. That's what we know. So where's zinc? Here's zinc right here. Oop, I don't want to make it so dark because I can't see the zinc. There's zinc. Okay, where are the other elements? Iron, right here. Copper, right here. Cadmium, right here. So What we know is elements in the same group have similar chemical properties, and a group is a column. So we would expect cadmium to have similar properties because zinc and cadmium are in the same group. That's a trend. And we'll learn in the next chapter how the electrons are involved in this, because in terms of the chemical properties, it's their electrons that are all involved. So we have one more trend, and it's also a new idea or concept to us. And it's something called ionization energy. And we're going to be doing some things with ions here in just a little bit. But ionization energy is how much energy it takes for an electron to be removed from an atom. So recall from electron configurations, we have electrons that are in the electron cloud outside of the nucleus. We know that the number of electrons equal the number of protons in a neutral atom, but electrons, unlike protons, their numbers can change. And we can add electrons and we can remove electrons from atoms. And the ionization energy is how much energy it takes to remove an electron. And so you can see the trend as you go across a group, the ionization energy increases, and as you go up a column, it increases. That means that these elements in the upper right-hand corner have the highest ionization energy, and these in the lower right-hand corner have the lowest ionization energy. It also means that it is hardest to remove electrons, or I should say requires the most energy from these, and it would be the easiest, or I should say requires the least amount of energy to remove them here. Now, into my mind, it makes sense because from a previous trend, these are the smallest atoms, and these are the largest atoms. So the smallest atoms, the electrons are held closely to the nucleus, so they feel a greater pull, so it's going to be harder to remove them. On the largest atoms, the outside electrons are very, very far away from the nucleus in electron atom terms, and so it's easier to draw them away because they don't feel quite as much pull from the nucleus as a smaller atom would. So let's see how we could use this trend to answer a question. So it says, based on the general trend, what has the higher ionization energy? So let's rewrite the trend on this periodic table. So as we go across any of the periods, our ionization energy increases. So on this side, we have the lowest ionization energy, and on this side, we have the highest ionization energy. Now, when we go up a group, if we can go up any of the group, it also increases. And so we would have the lowest in the bottom and the highest ionization energy on the top. So let's find out where our elements are. The first is lithium and sodium. Okay, so I know in a group, if I look here, I know that the ionization energy increases up a group. So what do they want? They want the higher one. So the atoms in the higher on a group would have higher ionization energies. So lithium would have the higher because it is higher than sodium, and we know it increases as you go up, the ionization energy. So the other one is oxygen and fluorine. So here's oxygen, and fluorine is next to it. So these are in the same group, the same period. And as you go across, the trend is the ionization increases as you go from left to right. So since fluorine is further to the right, fluorine would have the highest ionization energy, and then oxygen would have lower. So that's all the trends we're going to go over, and we'll be using some of these trends as we move forward. For me, the easiest way to grasp the trends is to get a periodic table and to draw the trends onto a periodic table so I can see them all together and to kind of start processing and see how they're connected. And if you would like me to, you're welcome to come by my office hours, or in class, we can get a periodic table and do that exact thing. Just write, how would all the trends look if I put them on a single periodic table?